Hi, welcome to lecture 5.5c. So today we're going to be talking about integrating trig functions. So when I say integrating trig functions, I mean a little more than what we already know how to do. We already know how to integrate, sine of x. So that's like a basic trig function. But we want to integrate functions which have combinations of sines and cosines, and we'll see combinations of secant and tangent as well. Basically, the main kind of template integral that we're thinking about is one like this guy, where it's an integral with sine to the some power and cosine to some power. So I could write this as like sine to the n of x times cosine to the m of x. So sometimes we write that just means standing in for any integral of that format, sine to the something, cosine to the something, and an m are like, positive numbers. So we're going to see some techniques for handling integrals like this. For these integrals, they look a little bit scary at first, but they kind of all end up working the same. So it just takes a little bit of practice getting used to the quirks. So we'll see that a lot depends on which power is odd and which power is even. Okay, so before we start, let's recall some identities. So it turns out, basically, the only way to do any of these integrals is to make clever use of this identity and the other two. So this one on the left is the most famous one. If you know anything about sine and cosine, you should know this. That when you square sine and square cosine, add them up, you get 1. Remember, that's secretly Pythagorean theorem. And then on the right side, these are just like some other identities involving sine and cosine. These are a little less famous, but you might have seen them before. These are called the double angle identities because like there's a cosine of 2x. So if I wanted to like figure out like a different way to express cosine of 2x, I could rearrange this as cosine 2x equals. Notice this is not a typo. The one that has sine in it has a cosine here, and the one that has cosine squared also has a cosine. So the only difference between these two is minus versus plus. So these are a little bit weird. You don't necessarily have to memorize them. You should just know that they exist and that they will be needed when you're doing this style of integral. For us, the main point of these identities is to be like reducing the power, right? We're focusing on these powers, the 3 and the 2. So if I had like an integral that has sine squared, I could just replace the sine squared with this guy, and that's easier to do because maybe I know how to do the integral of cosine, and it turns out we can deal with a 2x. It's not too bad. So we'll see how that works all going forward. Let's just start with this example. So like I said, it kind of depends on what the powers here are. I'm just going to show you how this first example works, and we'll kind of generalize a strategy from that. So we're always going to start with a u sub. Let's just try u equals cosine. Like I said when we were talking about u sub, you can always pick different things. Maybe in a minute we'll look at what happens if you pick sine. But let's see what happens if we pick cosine. Then I do my du. Derivative of cosine is negative sine. And I like to rearrange dx equals du over negative sine of x. So it's important here that we're dividing by sine. We'll see what happens. In our integral, sine cubed stays for the moment. What's cosine squared? Well, it's u squared because we said u was cosine. So this is u squared. And then dx becomes du over negative sine. Okay, so now notice what's happened here. We had 3 sines on top, and because of the u sub that I chose, we get 1 sine on the bottom. So one of them is going to cancel. This is actually a big deal because before we had 3 sines on the top, and 3 is a little bit annoying. It turns out when there's only 2 sines on the top, when there's an even number, it's actually way easier to deal with. So the reason we picked u as cosine is that when I do my du, I'm going to kill one of these signs and change the 3 to a 2, and we will see that having the powers be even is way easier. So already that suggests something, right? If the integral was instead like sine squared cosine cubed to start with, then u equals sine would be the right choice, because when we take the derivative, right, we'd end up dividing by cosine, and we'd turn this 3 into a 2 instead. Okay, let's see what the cancel looks like and why it's a good idea to have sine squared instead. First of all, we can pull this negative all the way out front, right? Negative 1 in the bottom, dividing by negative 1 is the same as times negative 1 out front. I'll have a sine squared, and I'll have u squared. Okay, why am I happy about this? We talked about this identity is that we're going to need it. We can rearrange this identity. I have a relationship, an equation involving sine squared and cosine squared. So if I ever see some sine squareds, I'm happy because I can rearrange it as 1 minus cosine squared. Now you could always do that. I could have done that at the beginning before any of this u sub or anything. But it's a good idea here to have cosines inside my integral instead of having sines. Right? Why is that a good idea? Because if I have cosines inside my integral, I changed it to du. All my cosines can become u's. Right? So let's see what this looks like. This is the integral of 1 minus cosine squared. That's just using the identity. By the way, it's good to have these parentheses like this, because if you didn't have them, it would look like, when I write the u squared, right, it would look like you're doing cosine squared times u squared, which is not what we mean. So we have to keep the parentheses. Okay, but now like we said, cosine is u. So just like we replaced the cosine at the beginning, I can replace the cosine right here. So it's 1 minus u squared. That's 1 minus cosine squared. I still have this u squared on the outside. All of a sudden, this looks like an integral that we're much happier doing, right? I can multiply this u squared through. I'm going to get u to the 4. And I can just power rule this. This is a totally normal integral, right? Keep the negative sign out front, and then just do each part separately. Plus 1 to the power, plus 1 to the power. And I'm basically done. Like, I've gotten rid of the integral sign. Just like with any u sub, the last step is to come back and put the u's back in. So for our final answer, we'll have cosine cubed over 3, and then minus cosine to the 5 over 5. And that's our final answer. I guess plus c. We could go back and check that if we take the derivative of this, we'd get the original. Okay, so whenever we have a sine to the something, cosine to the something, the same setup is going to happen. I want to pick a u, which turns the odd powered one into an even powered one, because I divide by the derivative whenever I pick a u. If sine's the odd one, then I want to pick cosine as my u, because I'll end up dividing by sine, negative sign. The reason I want the sines to be even power instead is because if they're even powers, I can use my identity, and the thing I replace it with, one part of it is always going to be the u that you picked. By the way, here it was a power of 2 specifically, so we replaced it with 1 minus cosine squared. I didn't really justify why you would want it to be an even power in particular. Like, power of 2 seems good because you do 1 minus cosine squared, but how could I do a different even power? Like, what if it was sine to the 4 or something? Let's see just a quick example of that. Suppose we had sine to a really big number, a really big odd number, like 101, and cosine squared. Okay. again, I want to turn this 101 into an even number. So let's pick u as cosine, du as negative sine. And the same thing is going to work. I'm going to have sine 101 x, cosine is u, dx will be du over negative sine. Just like before, one of the signs cancels, so negative sine to the 100. Okay, so now I want to use my identity, right? Sine squared is 1 minus cosine squared. Since cosine's u, I could even just write 1 minus u squared at this point. So I want to put this in here to turn the sine stuff into u stuff. So it's not literally sine squared, but how could I get to sine to the 100? Right, basically notice sine to the 100, it's actually a bunch of sine squareds, right? What if I wrote it as sine squared to the something? Right, you gotta remember your exponent rules, but I can actually put a 50 right there, right? If I have 50 sine squareds in a row, that's the same as sine to the 100, because we multiply these. So that means, and I can only do that if it's an odd power. Like if it's sine of 101, sine to the 101, I could maybe split that as sine times sine to the 100, which would maybe be sine times sine squared to the 50. So I could still do that part, but I have this extra sine here, which doesn't work, it turns out. But when it's exactly an even power, I can directly sort of factor it as sine squared 50 times. And now we're happy, because this is 1 minus u squared to the 50. And, this is actually not super great, because I would have to do 1 minus u squared to the 50. There's actually another substitution you could maybe try that would help. Maybe as a bonus problem, think about v equals 1 minus u squared. I think that works. I have to think about that. But anyway, the point is we want an even power because I can do this trick here. Okay, so that strategy works for any integral of this form. Sine to the something, cosine to the something. It's not really different whether sine or cosine is the one with the odd power. You just have to figure out which one is the one with the odd power and use the other one as your u. By the way, it might be slightly instructive just to see what happens if you pick the other one. So let's look at this integral again. Say we picked u as sine. We'd get du is cosine. And we'd get dx is du over cosine. So my integral would become, so sine is u, so I'd have u cubed. And then I'd have cosine squared. And then I'd have du over cosine. So one of these cosines will cancel. But this is kind of a problem. So this is cosine of x. This is kind of a problem because I don't have any way of dealing with this cosine. I can't use this. You could try to use this. I could try to solve for cosine equals, but I'd have a square root show up and it would be kind of awkward. So we always want to pick the other one, and it's way cleaner. Okay, so let's keep going. This example I mostly included for completeness, but it's exactly the same procedure as the other one. I'll do it quick so you can see now that we know how it works. So the power of cosine is odd, so I want to kill this cosine, so I'll pick u as sine, du is cosine. We can rewrite this as u to the 4, cosine to the 5, and then the du is going to be, or the dx is going to be du over cosine. And one of them will cancel. So we'll get integral u to the 4, cosine to the 4. But now this is cosine to the 4 is cosine squared. And cosine squared squared is 1 minus sine squared squared. But because we said u was sine, this is 1 minus u squared squared. So we have 1 minus u squared squared du. This should be a u, sorry. Okay, so now we're almost done. We just have to multiply everything out. Let's keep u to the 4. Let's FOIL this. It's going to be 1 minus 2u squared plus u to the 4. And then we keep distributing u to the 4 minus 2u to the 6 plus u to the 8. Yeah, there's some big exponents, but it's totally fine because we can just power rule each of these, right? U to the 5 over 5 minus 2u to the 7 over 7, just plus 1ing these, u to the 9 over 9. And then final answer, we just plug the sign back in. So it's a little bit of writing sometimes, but you can do it. Plus c. So sometimes this multiplying out part can be slightly tricky. You just got to be careful, but you can do it. By the way, you might wonder how I did this part so fast. Just remember, if you ever have a good like algebra thing to sort of have in your head, is that if I ever have something plus something squared, like I FOIL this, right? A plus b, I'm going to get a squared plus ab. Or I guess that error didn't really mean anything, but plus AB. And then you're going to get another AB, right, from here. And then you'll get a B squared. So you always get two of these. So a good just like algebra thing to have in your brain is that A plus B squared is A squared plus 2AB plus B squared. And that works even with if it's a minus sign instead, right? So like here, in my head, I'm thinking, okay, this is A, this is B, so I'm going to have A, and then 2 times AB, well, that's negative u squared times 1, so minus 2 u squared, right? And then B squared is negative u squared. You square that, you get u to the 4. Okay, so again, same as previous one, but we did cosine instead, so. Okay, so we want to consider like anything of this form where one of them, for any numbers, we just covered the case where one of the powers was odd. It turns out that if both the powers are odd, then what we have here is going to work just fine. If both of the powers are even, then it's actually not going to work because we don't have this thing where I can divide one of them away and then use this identity. So it turns out that if they're both even, or like if it's just cosine squared with nothing else, right, then we have to use these other two identities that we mentioned before. So let's take a look at this one. So it's sine to the 4, cosine to the 4. So it turns out it's just kind of a plug and chug where we replace these with those identities up there. So the identities were sine squared is 1 minus... By the way, it's easy to be lazy and just write sine squared when you really should write sine squared of x. Mostly it doesn't matter, but here it actually really does matter because the right-hand side of this identity has a 2x. Like this is x and this is 2x. It's different. If you... Like at the end when you're plugging in numbers and stuff, you end up doubling the input. So it matters. We also had cosine squared of x was 1 plus cosine 2x over 2. So we just have to sort of blindly, basically, plug these into our integral wherever we can. So just like we did before with the even powers thing, maybe notice that this is sine squared squared, and then this one is cosine squared squared. So we're going to put our identities inside both of those squared things. So here, first we'll do the first thing squared, and then the second thing squared. The first thing is sine squared, so I'll put 1 minus cosine 2x over 2. And this one's the cosine one, so we put 1 plus cosine 2x over 2. So there's no real trick to these ones beyond knowing that you're supposed to use these double angle identities and then being willing to plug and chug a bunch of algebra. I'll show you a couple tips to make the algebra go faster. First of all, when I square a fraction, I square the top and I square the bottom, right? So this is the same as 1 minus cosine 2x squared over 4, and then 1 plus cosine 2x all squared, also over 4. So I have two of these over 4s, so it's totally cool to just pull them both out in front of the integral, and they'll multiply together because they're both on the bottom. So you get 16. Cool. And then what you have left over is the 1 minus cosine 2x squared, 1 plus cosine 2x squared. You can just FOIL this out. I will show you a nice trick, which is that, remember, whenever you have like something squared times something else squared, it's the same thing as take the first thing times the second thing and square that whole thing. So here we have something squared times something squared. It's going to be the same thing as 1 minus cosine 2x times 1 plus cosine 2x. And then the whole thing is squared. So there's different routes through the algebra. You could just FOIL them. If I FOILed the first thing, I'd get 3 terms. If I FOILed the second thing, I'd get 3 terms. And then I'd have to multiply them together, it'd be like 9 terms. It'd be kind of a pain. This is a nice shortcut because there's another nice algebra shortcut about stuff that looks like this. So remember, if ever you have, I think we talked about this one last time, if you ever have a plus b times a minus b, then when you FOIL, you end up with a squared minus ab plus ab minus b squared. And these cancel. These middle guys cancel. Sorry, this a squared. The middle guys cancel. So you always end up with a squared minus b squared. So if I see this 1 minus cosine, 1 plus cosine, it's not that much like a weird trick to remember because it comes up whenever you use like multiple of these identities together. I can just change this into a squared minus b squared. So like if this is my a minus b, a plus b, right? Then I'll have a squared, which is 1, and then minus b squared. So b squared is cosine squared. Remember, that's all still inside these parentheses where we have to square the outside. So again, you don't necessarily have to know all these little tricks, but it can be done fairly efficiently if you make use of them. Again, you could just FOIL them out. It would just take a little bit longer. Okay, we got to keep going. At this point, I do just kind of have to FOIL, so let's do it. We can remember our FOILing shortcut from before, which is this is always a squared plus 2ab plus b squared. So here we're going to get like this is a and this is b now. So the role of a and b sort of change. So we'll get 1 minus 2 times 1 times negative cosine, or cosine squared 2x. So that's the AB, and then plus cosine to the 4. Okay, so what ends up happening when you do these integrals with even powers is that they're very annoying and they take forever because you have to sometimes do multiple things in a row. What was the point of all this work? We got to this integral that's supposed to be an easier integral to do. I bet we can integrate this part. How could I integrate this part? Ah, I got to use my identity again. So it's a little gross. But we can do it. After I integrate that one, how do I integrate this part? It's cosine squared squared, and I got to use my identity again. Right, so it's a little bit of a pain. But let's just kind of keep going, plug and chug, and see what happens. First of all, let's keep our 116. Let's just try to kind of stay as organized as possible. This 1, I can integrate it right away, and it's going to become an x. So I'm going to have it become x right there. But then I'm going to move the integral sign through and sort of put it on the inside stuff. Right, I can separate this into two integrals. So it's easy to kind of lose track of where you're at, but here we are. Let's just focus on this one for a second, and then we'll maybe come back and plug it in. So let's move off to the side here. So we need cosine squared 2x. Now we basically just have to use our same identity as before. So this is I wanna use my identity, which was this guy, cosine squared of x equals that guy, right? We have to be a little bit careful here because this cosine squared, it has a 2x inside it already. That means I'm going to have a 4x when I use my identity. Let's think about that. Cosine squared of x is equal to this. So that means whatever I plug in for x, I'd have 2 times that x, like on the right-hand side of my identity. So if I already have 2x in there, it'll have 2 times 2x right here. And I'll have 4x. So we're going to get 1 plus cosine of 4x all over 2. Again, we can pull the 1/2 out front. 1 plus cosine 4x dx. We're almost done with this part. Again, we can integrate this 1. So let's leave the 1/2. The 1's going to become an x. Now I have to integrate cosine of 4x dx. Now it's tempting to just write sine here, but we should think about it, right? It's not cosine of x, it's cosine of 4x. I technically don't know how to integrate cosine of 4x. I just know how to integrate cosine of x. So we technically have to do a little u sub right here. Let's pick u to be that inside 4x, because I'd rather that just be a single variable u, right? If I do du, I'm going to get 4 dx, and dx is du over 4. So this little integral becomes cosine of u du over 4. I pull the 1/4 out, and then when I take the antiderivative, I'm going to get sine of u, but u was 4x. Okay, so this is like a little dance you have to do sometimes when you're just integrating like cosine of something that's not just x. Notice that basically what happened is I did get to write sine, right? Sine of 4x. But I have this divided by 4. And you think about that, it makes sense, right? Sine, if I take the derivative of sine 4x, I get cosine 4x, but then chain rule says I have to times by 4. So when I do the antiderivative, I have this division by 4 instead of that multiplication by 4. So if that makes sense to you, it's totally fine just to jump straight from here to here. But the way to show that that like is legit is this little u sub. And if you forget, you can always do the u sub. Okay, so let's kind of continue our equals sign. I'm going to have 1/2 x, that's the same. Then I figured out this integral. It was 1/4 sine of 4x. Now, notice how easy it is to mess up the fractions here. Like I have this 1/2 here and this 1/4 here. But like this dividing by 4, it only actually like applied to this integral. If I had like tried to do the u sub up here, I might have accidentally put the divided by 4 over the 1 also, and I'd have the wrong number. Not to mention the fact that I'd also be distributing, right? Like if I distribute this through, I'll have a half x and then an eighth sine 4x. And this is all inside, really, a big thing which has a 16th out in front, right? So it's easy to mess up the fractions and stuff. So we just want to just write it carefully and, you know, give yourself plenty of paper. So with the answer to this integral in hand, this one, let's kind of come back and continue our line of thought. By the way, I know this is like a super long integral. Most of them aren't this long. I want to do this long one to kind of show sort of the same thing happening several times. But most of the time, you know, if you just need to integrate, like, what's the integral of sine squared of x? That's like the most common use case. And it's the same process here. It'll just end up being shorter. So if I don't have this one later in the notes, I encourage you just to try this one. Maybe even right now or after we finish this maybe, to see that you can do it in a couple steps. Okay, sorry, tangent. We're finishing this equal sign, so we just copy everything. Except this integral, this cosine squared 2x, we figured out it was this guy, so we got to copy that. Whenever I'm putting in a big chunk of algebra, I like to just throw in a new parentheses, just so I don't get confused. Like there's this 2 here in the 1/2, right? So I got to make sure I'm doing that right. Inside these big parentheses, I have this 1/2 new little parentheses, right? X plus 1/4 sine 4x. And you know, I could have distributed that 1/2, you know, but whatever. You can always distribute later. And then we still have this other integral that we have to do, this cosine thing. So let's actually grab this integral also and kind of work on it and then come back. So we're going to come down here. So we want to do the integral of cosine to the 4 2x. And I bet we can see where this is going, right? We have to write it as cosine squared squared. And then I got to use my double angle identity here. Remember, there's already a 2x in it. So I'll do my replacement. Cosine squared becomes 1 plus cosine over 2. And remember that I had a 2x already, so that when I double my angle, I'm going to go to 4x here. Same logic as we did earlier. Cool, so that's cosine squared. I have that whole thing squared. Okay, just like before, I'm going to square the 2 in the bottom, give me a 4, and I can pull the 4 out of the bottom. So I'll have this. On the inside, I'll have 1 plus cosine, and I got to square that, right? So it'll be like 1 plus 2 cosine plus cosine squared, right? So that's, I'm foiling that. 1 plus 2 cosine of what? It's cosine 4x. And then plus cosine squared of 4x. Okay, this is a marathon problem. We're almost there though. Keep the 1/4. The 1 becomes an x. How do I integrate 2 cosine 4x? Well, this is the same thing we did before, where it's technically a little u sub, right? Our shortcut we learned was that it's going to become sine, but then I divide by 4. So I have this 2 already, so I'm going to divide by 4, and I'll have sine. Okay, and then this last part, I have to integrate one last time cosine squared of 4x. Again, we just have to replace it. So this integral is same identity. Cosine squared becomes 1 plus cosine of double the angle. So I'm going to get 8x here, right? And then over 2. To scroll. So again, here we can pull the 1/2 out. The 1 is going to become an x. And then I have to integrate. I kind of did a few steps there, so let me write this down. Right, we pulled the 1/2 out. The 1 becomes an x. And I still have this integral left to do. Same logic as before. This is going to become sine of 8x. But then I have to divide by 8 because of that 8. So all of that annoying stuff is this integral right here. So maybe let's just write our final answer from this part. So this will be 1/2. I'm simplifying the 2/4. Sine of 4x plus this guy, 1/2 x plus sine 8x over 8. Need 2 parentheses at the end there. Okay, before plugging all this back into our big integral at the top, let's go ahead and simplify as much as we can. Notice this part is going to be 1/2. Like if I distribute this 1/2 through, I can have a 1/2 x here plus a 16th sine. And then we still have this other stuff. So when we distribute the 1/4 through, it'll look like this. We'll have 1/4 x, 1/8 sine of 4x. Now I got to put that 1/4 on these last two terms also. So I get 1/8 x. And then 4 times 16, whatever the heck that is, 64 sine of 8x. Okay, definitely a mouthful. Can we simplify anything? The x's can go together. So I have an 1/8 sine of 4x plus a 64th sine of 8x. I can't combine those, sadly. But how much x do I have? I have a 4th plus an 8th. A 4th is 2/8, so I have 3/8. Okay, so that's a big thing that we can grab and put inside our other integral. So let's grab that and come back up here. Yeah, so definitely a lot of work, but I think we're pretty much done. How do I... Sorry, I forgot how to paste. Paste? Okay, great. Okay, that was the result of this cosine to the 4 integral. Great, kind of gross, right? Let's just finish off to get a satisfying answer by distributing everything through. Let's just focus right here really quick. I can distribute the 2 through, and it actually just cancels that 1/2. So I basically can ignore that. So we're going to get 1/16 x, and then minus x minus 1/4 sine of 4x. Right, because of the 2 cancels, and I just have the minus sign. Okay, so plus blah 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 blah. Let's combine all what we can combine. So we have some x's and we have some sine 4x's, right? How much x's do we have? We have a 16th of them. By the way, this is a good way to like combine terms. I'm seeing I have this x, I have this x, I have this x. I just want to count how many I have. This is technically factoring the x out, but I'm just thinking of counting. I have a 16th x, I have minus 1x, and I have also 3/8 x. Whatever that fraction turns out to be, that's the total amount of x that I have. Same thing for the sine 4x. I can count. How much do I have? I have negative 1/4 for the first one, and I have an 1/8 for the second one. And that's how much sine of 4x I have. And then I think I have just this one term plus a 64th is how much sine of 8x I have. Okay, so just maybe finalizing the fractions here. This 3/8 is 6/16. This -1 is -16/16. So in total I have so 1 minus 16 is -15, and then plus 6 is -9. So that's how much x I have. And then over here, 1/4 is 2/8, so I have 1/8 minus 2/8, so I have minus 1/8 sine 4x. So yeah, I promise this is way longer and more annoying than any problem I'd expect to do on an exam, but it's a good showcase of all the different little algebra tricks and u-subs and little things that can happen when you do these types of integrals. Again, with some of what we've done in mind, go ahead and try, just do sine squared of x and just see what happens. It'll be a lot simpler. Okay, so that covers all the possible cases for sine and cosine. We know what to do if both powers are even. We use these identities and just plug and chug forever. If one is odd, we use u sub. And actually, if they're both odd, we can use u sub anyways. The next group of integrals we're going to look like is the same sort of format, but with secants and tangents instead. So, for example, this integral here, secant to the 4, tangent to the 4. By the way, even though they're both even powers, this one's going to be way easier than the last one. So, just a reminder, if you've forgot, tangent is just another name for sine over cosine, and secant is just another name for 1 over cosine. The tangent and secant have their own identities, which you can prove coming from the sine and cosine identities. They're basically just the same identities, but rewritten using these fraction versions. So you might not know this one off the top of your head, but it's a true identity. Tan squared plus 1 is secant squared. You should think of that as kind of like the Pythagoras one. Sine squared plus cosine squared is 1, but for tangent and secant. Something else that we need to know is about the derivatives. So the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. So you can just check those. If you use these definitions over here and do like quotient rule and stuff, you can prove that. We'll need those when we do u-subs. Okay, so let's see what happens in this case. This is going to be very similar to the first problem that we did. Again, I'm just going to pick a u-sub, and we'll see why it works, and then talk about why that was a good u-sub to pick. So let's try use tangent. Why is that a good idea? Well, before, the point was when you do du, you end up dividing by the derivative. So what's the derivative? It's secant squared. And du or dx, you can divide, is du over secant squared. Okay, so one of a secant squared is going to get canceled out. I have 4 secants. I'm going to lose 2 of them. I'm going to have a secant squared sitting there, and hey look, secant squared, tan squared. Just like with the sine and cosine squared, I'm going to be able to make a substitution. So let's see what that looks like. So keep the secant squared for the moment. Tan is u now, because we substituted. And then dx turns into du over secant squared. Sorry, this was secant to the 4, excuse me. So 2 of those will cancel. I'll have secant squared on top and u to the 4 du. Now I can use my identity and turn secant squared into tan squared plus 1. So again, you have to know that identity, but whenever you're doing secants and tangents, you should have that identity in the back of your mind, or look it up if you don't remember. Know that it exists is the main point. Okay, so same pattern as before, right? We turn it into a tan, but that's our u. So this is the integral of u squared plus 1. Now I'm totally happy because that's an integral that we can do. U to the 6 plus u to the 4. And we could just integrate. So plus 1, plus 1. And we just got to plug our original u back in. So tan to the 7 over 7 plus tan to the 5 over 5. So that's an integral we could do. So pretty much the exact same thing. It only worked out so nicely because we picked the right u. So if you want to like memorize something, if the power of secant is even, then u equals tan is what you should pick. If the power of tan is odd, as we'll see in this example down here, you'll want to pick u as secant. But it's the same idea as before, where whatever you pick for u, you'll divide by its derivative. That's going to change the even one, the secant one, into still an even one, but smaller. Okay, so let's see what happens when we try this one. So here the power of tan is odd, so let's try u equals secant. I got another derivative of secant. It's on the top of the page. Secant times tangent. Again, you just have to know that. It's a little weird, but that makes dx du over secant times tangent. So when we come to do our integral, secant squared is u squared. I have tan cubed for the moment. Dx becomes du over secant times tangent. One of the tans will cancel. And this secant is actually u now, right? So it's going to cancel with one of the u's up there. So I'll have a single u, because I really have a single u in the bottom. And then I'll have tan squared left over. Now again, we want to use our identity. The identity is a relationship between tan squared and secant squared. So I can always solve one for the other. Tangent squared is secant squared minus 1. So my integral is going to be, and this is u here, right? U squared minus 1. So my tan squared is going to become u squared minus 1. This should be a du, sorry. It's a du. And that's an integral I can do, right? Multiply through. And I believe you can do that one. Give it a shot. Okay, so same sort of strategy. You're hoping to make a tan squared or secant squared pop up because that's what you can replace. There's a little bit of asymmetry here. When you pick u as tangent, right, you end up dividing by secant squared. So here I'm hunting for a secant squared because I want to use my identity here. So dividing by secant squared is good because it makes it smaller. Here, the derivative is secant of secant. The derivative of secant is secant times tangent, so it kind of gets rid of one of the tangents and one of the secants. So there's a little bit of funniness going on with the numbers there, but it kind of just takes some practice doing a couple problems and seeing how it ends up working out. Okay. There's a few similar tricks we can do. So so here we covered power of tan is odd, power of secant is even. Let's look at this one. There's no secants at all. The power on tangent is even. So again, we have our identity. Tan squared plus 1 is secant squared, which if I want to, I could always rearrange. Tan squared is secant squared minus 1. So it turns out here, it's actually not too bad. It turns out to be easiest to leave things, to kind of turn stuff into secants, for the basic reason that I actually know the antiderivative of secant squared? It's tangent. Because we recalled on the earlier page that tangent's derivative is secant squared. So if I ever see just integral secant squared, I get tangent. Similarly, if I have integral secant squared, secant times tangent, that's secant. Those are actually sort of elementary ones that we maybe are supposed to know off the top of our heads. So if I can use my identity to turn this into like a bunch of secant squareds, I'm going to be happy because I'm going to be integrating secant squareds, which is something I know how to do. So let's try this. Similar sort of trick as before. Tan to the 4 is really tan squared, right? So using my identity, this is secant squared minus 1. That's this tan squared. And notice I'm not really going to be doing a u sub, maybe at least not yet. Let's FOIL this. Actually, I think I actually screwed up. Let's see what happens when we FOIL this. I'm going to get 2 secant squared plus 1. So this is a good lesson. This part I can do, like by over here, and I can integrate that. But integrating this actually sounds maybe just as hard as integrating this one in the first place. It's just some secant by itself. So I forgot that on this example, we actually want to do something slightly different. I don't want to turn all the tangent squareds into secant squareds. It turns out the right way to do it is to turn one of them into secant squareds and leave the other one. So this is a little bit subtle, kind of thing you have to do a couple times to remember. All right, tan to the 4, it's tan squared times tan squared. Let's just replace one of those. So it's not super obvious that this is the right way to go, but let's just see what happens. So the first one, say, becomes secant squared minus 1, and then times tan squared. Okay. Let's distribute this through. Secant squared times tan squared minus tan squared. Okay, so there's a few things going on here. First of all, we might as well separate this into two integrals and just do them separately. So let's write it like that. So dx and then plus this integral. The one on the left looks a little funny, but it's actually not that bad because we know this guy. The derivative of tan is secant squared. I have a secant squared sitting right here. So there's a piece of my integral whose derivative is sitting right there. That means it's a good u sub choice. Let's try u equals tan. Du is secant squared. X dx. And so dx is du over secant squared. So this integral is going to become, right, secant squared. Then tan becomes u, so u squared. And dx is du over secant squared. So those are going to cancel. Totally happy with that. U squared is just going to be u cubed over 3, right? U is tangent, so it'll be tangent cubed over 3. So we can totally handle that first integral, no problem. For the second integral, at first it looks a little bit mysterious. Integral tan squared, how do I do that? Like, I know the integral of secant squared, but I don't know the derivative of tan squared. Well, remember, we can always translate between secant squareds and tan squareds, just like you can translate between cosine squareds and sine squareds. The integral of tan squared is the same as the integral of secant squared minus 1, because that's what tangent squared is. But I'm totally happy with this, because I know the antiderivative of secant squared. I know this part. We're talking about that. That's going to be tangent. And the minus 1, that's just going to become a minus x. So, yeah, these tangent secant ones are a little bit trickier. Sometimes you have to play around and try some different substitutions, some different using of the identities, but it's all going to be like in this universe. You're going to use these identities. You're going to use what you know about the derivatives. Maybe try a u sub or two. Sometimes you have to play around to get it, but it's all in that vein. And I think this strategy will always work. I just kind of momentarily forgot. If you can get it down to, if you can get one of the tan squareds, then you can do this translation, and your u sub thing is going to be useful. Okay. So let's just look at one more, and I'm actually going to not go through this one totally. I'm going to leave it as a sort of a challenge problem. So it looks similar to this one. We had a tan to the 4. Here we just have secant to the 5. It looks sort of innocuous. It just turns out this is kind of an annoying, like, integration by parts sort of thing. So I'm going to leave this as maybe like a challenge if you want to try. A hint is that at some point you'll have the antiderivative of secant by itself, and you kind of have to look this up or know that the antiderivative of secant ends up being this. It's weird, right? I mean, antiderivative of secant squared is easy. We just did that. It's tan, right? But secant by itself is actually a little weird and ends up having this guy. But you can set this up as a by parts problem. Try u is secant cubed, and dv is secant squared. So if you want to try that, go for it. But this is an example of, it's a little bit harder than I would expect to do, definitely on like an exam. The main thing I would want you to kind of be able to do, semi off the top of your head, would be something like, maybe this very first one, you know, with a 3 and a 2, I do u equals cosine, kill one of the signs, and I have this like u squared minus u4 kind of thing. That's kind of my expectation, and if you know a little bit about the secants and tangents, that's great, but those are a little bit trickier, and they actually become pretty tricky pretty fast. Cool. Yeah, so that's all I think I have to say about the trig power integrals. So thanks for listening, and I will see you next time.